Hello YouTube. Well, today we're going to take a look at these power meters of various varieties. So just kind of for reference, I have, here's the one I took apart and reverse engineered. I'm not actually entirely certain where the plastic for the cover went. It's somewhere in here, but yeah, I haven't been keeping track of it too hard. Don't really care. Anyways, let's just kind of go through these in sequence, just do a little comparison. Let's take a look at this, which is kind of our China special, I suspect. So what we have here is something that looks remarkably similar to the Kilowatt power board, display board, and you can see that we have, so this one has non-volatile memory, which is why it has this little battery. Current shunt, I believe that's a fuse, yeah, F1. You know, capacitive dropper. And then one of the things you notice is that this one, the plug section is kind of a unit, so they can put different plug sections, into different, you know, basically they can swap out the plug section. Right. See, there are just two screws, it appears. So one thing that is kind of neat on this one that I think I may investigate at some point in the future is if you look here, it's actually labeled VCC, ground, freak, clock, SDO, and SDI. So this may have, you know, obviously there's logic on both boards. And actually there we go. So it looks like this has proper dedicated energy management IC of some sort. So the pin is, the IC is completely unmarked. So you can see here's, you know, basically one line terminal input. So we have one line terminal and the other line terminal, so this is basically the creepage distance here. And then so the line terminal comes here, there's a fuse to this terminal. Correction. So power comes in, you know, so this is the current monitoring. So it comes in here, runs through the fuse. This fuse carries 15, this is, oh geez, yeah, look how heavy the cabling is on this. So this is like a 15 amp fuse, I'd imagine. And then for the power supply, it looks like it goes to this diode. There's a diode down there. That's probably part of the reactive dropper. So the cap is here. Got two caps across it. This is presumably the potential divider. I don't know why there's two of them. They have two completely separate potential dividers. This goes to a V here, and the other one goes over to this transistor. Oh, I bet one of these, this section here goes into this transistor, and that's the frequency thing. So I bet it's basically just when the line, you know, when you're positive, it turns this on, and vice versa. So that's just so that they have a 60 hertz or 50 hertz input. But the other one goes through that via there, runs all the way across over to here, I believe, and then just goes into this IC. So I don't know what this part is, because it's, as you can see, these two leads here are for a crystal, and the crystal is 4.096 megahertz. But that is, all the power monitoring ICs I'm familiar with don't have that pin out. You can see we have, looks like they're tapping off here and here for the reading back the shunt. Here's the shunt, incidentally. Kind of a little wibbly-wobbly thing. So down here we have, man, this is just, it's another 78L05. Man, I guess they must really like these, or they're really cheap in China, I don't know. So this also has a mauve. That's quite interesting. It's a chunk pretty decently sized. It's a fairly thick mauve, if not necessarily that heavy. You got a big cap, another big cap. These are probably bypassing. Yeah, so very similar. I don't think I'm going to go too in depth into these, just because I just want to kind of give an overview of what they all are. just kind of as a compare and contrast exercise rather than an in-depth reverse engineering. So here's the main board. Very similar to the Kilowatt. We've got a big cob, what looks like an RTC crystal, and 24 CO2. So this is just a little tiny EEPROM. So again, that's probably the cal. One thing of interest is if you look at this board, look, they used fancy curved traces, and then not. Kind of an incoherent board. And then here are your buttons. You can see there's a little reset button and so forth. So that's a very simple, it's very, everything is done by the energy management IC in this microprocessor. There's nothing else, really interesting in this board, if you will. It's very kind of plain Jane vanilla. Alright, let me just plop that back together. Oh, it's worth noting that for the Modlet power plug thing, I finally got the Linux. There's an open source kind of Linux done in Ruby for some godforsaken reason toolkit that talks to it and lets you pull the information without using their huge cloud pile of shit. And that makes it kind of a lot nicer if you entirely roll your own. You have to roll your own graphing crap and everything. I'm not really going to go anywhere with it, but I got it working, and it looks like it logs power usage on a second-to-second basis, and then stores it for you to then query later. I don't know how long it'll log before it starts dropping data, but yeah, so that's the way that works. And you can, run a command line command and, turn it off or turn it on or whatever. Pain in the ass. Ruby's, I don't know, why would people do Ruby? Ruby's looks like, it's like a modern language and fucking Pascal had like a bastard child. It's like, hey, I've got a great idea, let's use begin and end, because that's not, totally, utterly dead since fucking 1980. Control flow. Hey, look, all these other nice languages, Python, doing control flow, in a coherent way with indentation. Let's add begin and end. Because stupid. And then they indented anyways, just to make it more bizarre. That should just kind of snap in. So one thing of interest is that this particular kind of style plug, you can buy this particular style plug for, basically every outlet style as far as I could tell. I was like searching around on eBay, and you can buy the exact same thing, and you can buy one that has, an Australian outlet, an Australian plug. You can buy one that has a UK plug or an EU plug or whatnot. So I guess I'm kind of tempted to buy one of the ones that has, a 240 volt internal, just to see what they're doing different. I mean, are they still using a cap dropper at 240 volts? Because I think that's a lot less efficient. Looks like they use the same screws. So this is a much older Kilowatt, and this is the Kilowatt EZ that I was mailed. There might appear to be a screw in there. There appear to be a screw there either. This was held shut with one screw. Joy. So, Kilowatt EZ. Whoops, sorry, I somehow managed to take one screw out of one and I swapped hands midway through. Stir. Fortunately, they do all use the same screw. Alright. So this is already kind of interesting because take a look. So this is kilowatt EZ old style kilowatt. And as near as I can tell, there's no difference. So that's quite interesting. I thought the kilowatt EZ was supposed to have battery backing. So this is, you know, microprocessor 24CO2 EEPROM. Both of these use an L2902 op amp, quad op amp, and I would bet, I may reverse engineer the circuit from this, but I would bet the circuit here is nearly identical to the one in the kilowatt I took apart, you know, on this one here. And actually, interestingly enough, so you can obviously see that this is definitely one version, and then we have another. This is the other one. And then there have been some projects on the internet, like there's this project called the Tweetawatt, which was kind of a silly project, but they took apart a kilowatt that was kind of in an intermediate stage. It didn't quite look like, it wasn't quite this old school layout, but it was also, it was very much, it looked like this, only with through-hole components for the, you know, the op amp. And what I will probably try to do is stick that picture in right here. So anyways, one interesting thing here is that these, so this, the kilowatt, the microprocessor is unmarked, I think, yeah. But on the kilowatt EZ, we actually can read that they did not buy unmarked micros. So that is a PRODIGIT ProDigit 539202223. Let me change lenses. So here we are. So you can see that's a ProDigit 539202223. So it's quite remarkable, the fact that these are two basically, you know, it looks like what you get for the extra bucks you pay for the kilowatt is not much. I mean, I would expect some of this additional stuff to be stuffed on here, but I guess not. Obviously you can see that it appears that these had the facility, or they made a model that had a relay, and they just blanked that out on some of the boards. Also this resistor is kind of, probably should be up like that. It was kind of smooshed down. Q4. You know, this is probably a 78L05, yep. So, you know, these two different kilowatt models, you know, there's an on semi, it's a JR3 2902, 2902. It's literally, it's very much the exact same product. You know, the micro pinout's the same, so I guess that means that this is probably also a ProDigit. We can see both of these have a 24, not the 24A02, not the 24C02, but they're both I2C EEPROMs. But yeah, so that's interesting. So the total sum difference between the kilowatt and the kilowatt EZ is absolutely bunkus. I'd be interested in getting a current generation kilowatt EZ. You know, I'm not going to buy it because frankly I'm kind of nonplussed with their kit, but it'd be interesting to see if the current generation kilowatt EZ looks just like the current generation kilowatt internally. It may be that the only meaningful difference between the two products is firmware, in which case they've got some brilliant market segmentation going on and they're dicks. So I will probably reverse this board at some point in the future. I'm not too sure. I'm kind of running out of caring. I have run out of fucks to give with regard to these things. You know, kind of here's what they are internally. I don't think I'm going to go that much further. So this should be fairly interesting. So this, as I understand it, basically just, well, hey. Where is that other upload? So I'm actually not too sure what this does, because I thought this was one of those things where when you had a sufficient load on the primary outlet, the secondary was switched. But this is just a desk lamp. It's only a 60 watt lamp, but most of these are much more sensitive than 60 watts. So I suspect what in fact it actually is, you know, again, it's got this USB connection. So my guess would be that if you apply 5 volts on the USB connection, it triggers the secondary. And actually, I think I can confirm that, if I don't mind being a horrible person. I was just thinking I would abuse the fact that the Regal scope I have on my bench has a USB output, a USB connection on it. But I'm also realizing that I have, yeah, it's not long enough, so I'm going to do that. So, is that a $2,400 piece of equipment you're using as a USB power supply? No. Yep. So obviously this is fairly simple. Just when you have power on the USB, it turns the secondary on, which is kind of silly, to be honest. I mean, I guess there's a use for that. I'm surprised it's like a whole product, rather than just like a, hey, this is what, I don't know. I guess people pay for it. Somebody bought it and sent it to me. So it's that and, oh hey, safe. It appears this is missing some screws. I always wonder about the life of things before they get to me. So considering that this doesn't do any current sensing, that means internally it can be a lot simpler. They may in fact just be driving the 5 volts into the relay coil because the relay coil provides sufficient isolation for safety. Or it might be weird. Wow, it looks like something happened in here. My, I wonder what the hell happened here. So this is actually really quite clever. So you can see here we have two, these are MOVs. And we have one MOV going from neutral to earth and the other MOV going from hot to earth. But the critical thing here is these two MOVs go to this pad right here. And then they run through this little white thing here to earth. And you know what this little white thing here is? I'm pretty damn sure it's a thermal cutout. That's brilliant. So what they have is they have the MOV protects them, and then once the MOVs start to heat up because you've got like a prolonged line high situation, the thermal cutout kills it. And then it's all just clamped together with heat shrink. That's a really neat way of doing that. It's a pretty clever little mechanism. And then over here we have what looks to be another MOV. I haven't figured out where is that. I haven't quite traced some of this stuff out. It looks, there's a cap here. You can see you have hot. That's interesting. So it actually looks like this cap goes through this cap, runs to this MOV terminal. So I think this is across, because it looks like there's a little, like a capacitive, it looks like they're using this capacitor as a capacitive, dumper, a capacitive dropper for the running the relay. Because this relay, if you notice, has a 48 volt DC coil. That's actually also kind of nice. You can see by having a 48 volt DC coil, they're going to have very little primary current, or very little coil current. So they can get away with basically just a little itty bitty cap dropper. This is a 0.22 mic cap dropper. So you go through here. There's a fuse in there, which I don't quite see how it's connected. Supposedly there's this other black thing in there, which appears to, I'm not too sure. And then on the bottom we have 2 diodes and this big IC. which looks like a bridge rectifier. Ah, spilled alcohol everywhere. Paper towel in a minute. I'll just let it evaporate. It's like 85 degrees here. So that is indeed a bridge rectifier. So one of the things you can see here is that our power comes in, and then the only connection to the USB port is this opto. So that's your primary isolation. And then it actually looks like they're using the opto to, they're using the secondary side in the opto to directly switch the current to the secondary of the primary, the coil of the relay. So they're just directly switching the coil current using the opto, which is probably fine, assuming that they pick the opto for that, and that shouldn't be that big of a deal to do. There should be plenty of optos which are good for that. Assuming it's only like 20 milliamps coil current, which is reasonable. Probably less, actually, considering it's a 50 volt coil. Should be very viable. Other things you can see here, so this is our neutral. So they're switching the hot, which is proper. You can see here the two relay terminals. So this is your hot. Here's your neutral. They have this big, this is a piece of solid core wire. It's like extremely heavy gauge. And then over here, here's your earth neutral, which they bring across as just a piece of stranded cable, I guess, because they ran out of board space. You can see decent connections everywhere. This is a pretty decent little box. One thing of note is that this relay is in fact only rated for 7 amps at 250 volts, whereas the back of this says 15 amp max. So I guess they're just assuming that if you're drawing 15 amps, you're kind of spreading it across. That's kind of a bad policy. Yeah, so I guess they're assuming that it's 7.5 amps per socket for the 15 amp load. So they're fudging on their numbers a little bit, which is kind of other than that, it's not much. It looks like it's just a straight up reactive dropper. One of these may be a Zener. I don't know why they have a bridge rectifier. Yeah. So these two sides are the input to the bridge. And then these two sides, these are the output. And then is your USB. There's the series resistor for limiting the current. So it only looks at the 5 volt on the USB. And you can also see the retention pins for this connector were actually not soldered down. That's kind of a bad design practice. So they're just through holes rather than plated through holes with some solder on there, which means that the connector can wobble a lot. It's a bad design. It also looks like this board was, I think it was probably hand soldered. I don't know where all this flux mass, but you can see some of these. That diode is a little bit cocked. This diode is kind of, the pads are wide and it looks like they had some room for slop, which is interesting. You can also see there's cutouts in the silk screen for some of these. Man, look at that. They're running the power right around the metal screws. That's kind of trippy. So I guess they're just, man, they are not keeping much creepy. I guess they're just assuming the screws are electrically isolated from anyone. You can't stick your fingers in there because, look at the total creepage distance you're going to have from this metal screw to that hole. Assuming I can pick the goddamn screw up. When that screw's in there, that's like 2 to 3 millimeters. You can't get to these screws easily when the thing's plugged in unless you put it in an extension cord. But that just seems like really bad practice. So those screws may, you have to basically kind of assume that these screws may be hot. Well, fuck, look, that screw is going to be hot. That's the neutral. This is the neutral, but yeah, that's terrible. Well, okay, it appears that I'm actually not entirely certain how this thing was held together because it looks kind of like there was never a screw in here. I mean, look at that. It looks like there's plastic broken out there. Yeah, I don't know what's going on. So the top screws may have actually been like heat staked. So this sits in here. Yeah, I don't know how this thing was held together. Because the top, there were never screws in there. You couldn't fit them through. Those aren't through holes. The only thing I can think of is... Oh, I know how this works. So these had pins. These had pins poking through. And then what happened, I bet, is they pushed those pins through these holes and then they heat staked them down. So heat staking is basically you have this like a plastic rod that pokes through the board like they had here, and then they have like this hot plastic, this hot metal bar that just kind of goes, and what happens is it kind of melts and mushrooms over the end of that rod. It's basically like a plastic rivet. You can see these are heat stakes here where they're just, I'll break one. So you can see that it's basically just a little pin that goes through and then is mushroomed out over the end. And they mushroom that out by basically smooshing it with a piece of hot metal that melts it. So I think this top section was heat staked down. Though I don't understand what prevented this from, you know, kind of flapping open like I think you might have seen it. I guess nothing. This may have been glued. It looks from this white section here, it looks like the casing may have been partially glued, which could have been a part of it. But that's interesting. It's quite a little interesting diddly bob. I don't see, well, okay, yeah, so then it's just your standard, you know, power supply. It looks like here are your Zeners, your diode and your Zener, excuse me, for just limiting your VCC. Because when there's no load, that'll basically just, it'll just charge up to whatever the full voltage is. Just basically by virtue of the fact that, you know, if there's nothing dissipating the energy, the cap will just charge up indefinitely because each time it just pushes, you know, whatever amount of charge you can store in 0.2 microfarads, you know, over to this, you know, it's like a bucket chain kind of thing almost. But yeah, so that's kind of a cute little board. It's a decent product. It's safer than most, or safer than a lot of these things. I mean, the screw thing kind of makes me uncomfortable, but at the same time I understand how that could pass regulations because, I mean, you're generally going to basically assume that, you know, if you have screws covered by stickers on the back of something, you can basically guess. You know, particularly since the, Alright, no, never mind. Yeah, so there's just a little opto isolator switching a relay, and that just lets your, you know, your computer or whatever, USB 5 volt on that, turn your appliances on. Of course, a lot of this would be, I mean, this would be kind of useless nowadays because like 90, alcohol over here. Like, I know my desktop doesn't turn off the USB 5 volts when the system goes to, you know, turns off. You know, half of the systems out there make a big deal about the fact that you can charge your, you know, your phone or whatnot. You can charge it even when the computer's off because it's still the 5 volt. It keeps enough of the power supply running that it can run, you know, USB 5 volt outputs. So, it's an amusing little thing. The surge protection in here is nice. The fact that they've kind of bundled the temperature cutout in so tightly that you don't have to worry about it as a safe, you know, you don't have to worry about your MOVs blowing out, which is in fact kind of MOVs catching fire is one of the big common failure modes. Anyways, hope you thought that was interesting.